In 2019, the chemical tanker Fairchem Philly was discharging cargo at Deer Park in Texas. Due to an imbalance in pressure, the vessel's cargo tanks swelled up, a bit like a balloon, until they just couldn't cope anymore and they literally burst. The PV valves that would normally deal with this sort of thing were simply overwhelmed. Fairchem Philly was a 479-foot or 145-metre chemical tanker carrying a split cargo of methyl isobutyl ketone, MIBK, and liquid hexene. MIBK is a colourless liquid used as a solvent for gums, resins, paints and things like that. Liquid hexene is also colourless and used in fuels and to make flavours, perfumes, dyes and things. Unlike MIBK though, liquid hexene has an awkward habit of absorbing oxygen, so it needs to be stored and transferred under a blanket of inert gas, in this case nitrogen. Anyway, to discharge its cargo, Fairchem Philly connected up 3 lines to the shore: an MIBK cargo line, a liquid hexene cargo line and a nitrogen line. The idea is that as you discharge the liquid hexene, you pump in nitrogen to fill the empty space, keeping a blanket of inert gas over the hexene the whole time. Nitrogen is pumped in under pressure from the shore. As long as you keep the pressure balanced, everything is okay. On the Fairchem Philly though, shortly after they started pumping, low pressure alarms activated. The crew opened up valves on the nitrogen line to increase the flow and stabilise the pressure. 10 minutes later, further errors showed up on the system indicating there was now too much pressure. There was so much in fact that the PV valves activated, attempting to let some of the pressure out, but they weren't enough to get it down. The sides of the tanks gave way, spilling pressurised cargo into the adjacent ballast tanks and forcing ballast water out onto the deck. Everything was quickly shut down and the entire operation halted. The cargo itself, now exposed to oxygen, was completely ruined, resulting in a $100,000 write-off. Investigations later showed that the nitrogen supply that they'd connected up was too powerful, exceeding the design parameters of the ship's emergency pressure relief system. A pressure relief system usually consists of 2 relief methods: PV or pressure vacuum valves, or a PV breaker. A PV breaker is the simplest, typically installed on an inert gas line and operated using a simple liquid plug. Basically, as the pressure inside the inert gas line increases, the water gets pushed down. Once the pressure increases so much that the water's gone, excess gas is free to escape, relieving that pressure. In the case of a vacuum, the water plug gets sucked upwards by the low pressure instead until the bottom of the pipe is exposed. Air can then get past, relieving the vacuum and keeping the system safe. You can easily vary the settings of a PV breaker by adjusting the pipe level and the amount of fluid. But, although they're fine for inert gas, they can't be used on a cargo tank. If you release the pressure in a cargo tank through a PV breaker, vapours would linger near the deck, creating a new hazard. So, for cargo tanks, we have the PV valve instead, or more specifically, a high-velocity PV valve. When it comes under pressure, it uses that pressure to safely blast the excess gas clear of the vessel. These valves are often grouped together high above the hull of the ship. Each one is connected to one of the cargo tanks, so they all operate independently. The line from the cargo tank leads up the riser towards the head of the valve, which is split into 2 sections. On the left, you have the pressure part, and on the right you've got the vacuum bit. The pressure head consists of a seal held down by a variable force, which could be a set of weights, a movable spring, or something like that. It's just something that you can adjust to set the relief pressure that you need. As the pressure in the tank builds, it applies force to the seal. If that force increases past the set limit, the seal rises, allowing gas and pressure to escape. The shape of the head is designed to maximise the velocity of the gas so that when it escapes, it's blasted high into the air, clear of any personnel in the vicinity. On the vacuum side, it works in a similar way, with a seal held down by a force. As the pressure in the tank drops, atmospheric pressure starts to push the seal up. When the pressure differential matches the vacuum setting, the seal is broken, allowing air in to release the vacuum inside the tank. So, why didn't any of these valves work on the Fairchem Philly? Well, firstly, the PV breaker wasn't in use because the ship was receiving nitrogen from ashore through the vapour return line, rather than using its inert gas system with the PV breaker. The tank's main overpressurization defence was provided by the PV valves. While the valves offer great protection, they're not designed to cope with high volumes. Fairchem Philly's PV valves could cope with approximately 17,000 cubic feet per hour, but the terminal's nitrogen line could supply up to 250,000. To lower the rate, you use a smaller diameter hose. The terminal recommended 2 inches and the ship recommended 1. Despite that though, on the day in question, a 4-inch hose was connected. The operation was completely reliant on controlling the flow of nitrogen using manual valves, rather than the physical limitations that would have been imposed by the smaller hose. After the initial alarms warning of under-pressurization, the crew opened the valves further to compensate. Pressure quickly built up, triggering the PV valves, but it was too much for them to cope with. The only way for it to escape was through a tank rupture. Due to the vessel's double-hull design, the outer walls of the cargo tanks were the inner walls of the ballast tanks. When the cargo tank ruptured, the ballast tanks became pressurized, forcing ballast water up through the deck vents. With containment broken, fresh air was free to enter the tanks, introducing oxygen which was quickly absorbed by the liquid hexene, contaminating the entire cargo. And that brings us to the end of today's video. If you enjoyed it, I recommend you next watch this one about how the inert gas system works on a tanker. Until next time, thank you for watching, and goodbye.